Hello everyone, this is AllLogarithmsEqual with a new production. The episode today will focus on the Euler Totient Function and many of its properties. Now, many of you are already familiar with this function, especially if you've watched Modulo, a series that remains. This Euler Totient Function, by definition, as you'll recall, it returns the number of natural numbers that are co-prime, or relatively prime, to n. So it takes one argument, and then, as an output, as kind of, what the function returns, it'll give you the number of natural numbers, starting at 1, that are co-prime to n. So, to unpack that a little bit further, what does co-prime mean, if you're not already familiar? It means these two numbers are co-prime if and only if they share no common divisor greater than 1. And in terms of notation, we can say that the GCF of A and B equals 1. Or simply, we can have A and B in parentheses, so parentheses A comma B equals 1. And that is just to show that the greatest common factor equals 1. Now, in some other cases, which you'll see below here, in some other cases, the greatest common factor is some other number. So the GCF of 25 and 15, it's fairly evident that the result of that would be 5, because that's the largest number that they have as a common divisor. It divides into each of them, If we take the GCF of 4 and 28, we end up with 4, of course, because 4 divides into 28. And finally, if we take the GCF of 3 and 34, we get 1. And that's partly because 3 is a prime number, but also because 3 does not divide into 34. And also, as an interesting point of the definition, 1 is defined to be co-prime to everything. So as a result of this, we can see that phi of 0 equals phi of 1, and they both equal 1, most simply. So that's just sort of a definition, something that arises from the definition. So now let's consider some examples of this. And in fact, I'm gonna choose some specific examples to get a point across. So in this particular case, let's say, suppose that n equals 5. Well, then phi of n would equal phi of 5, so it would be the number, the number of members of the set of natural numbers from 1 to 5 that are co-prime to 5. And so in this particular case, we can go through and count them if you want. We can say 1 is co-prime to 5, 2 is co-prime, 3 is co-prime, and 4 is co-prime. So the result of that would be 4. And where n equals 11, we can, again, list out all the natural numbers up through 1 to 11, or from 1 through 11, and eventually we'll determine that each of them is, in fact, co-prime to 11. So phi of 11 equals 10. And we can keep going. Let's say n equals 13. This is another specific case where we know that all these numbers up to, well, basically less than 13, all these natural numbers less than 13, are co-prime to 13. So phi of 13 equals 12. And similarly, for n equals 17, another common example, we can go through each of these numbers and check that phi of 17 equals 16. And so why is this in particular true? Well, in fact, more generally, phi of n equals n minus 1 if and only if n is a prime number. And that should be somewhat intuitive, I think, because, the fact that it's a prime number means it has no factor. It has no distinct factor less than it, that divides into itself other than 1. And even 1, we count 1 as being co-prime to everything. And the only reason we're subtracting 1, in fact, is because no number is co-prime to itself, or else that wouldn't make any sense. So phi of p equals p minus 1, as a generalization. And as a final remark on that, this is really quite interesting, and that's because every whole number... Oh, hang on. Well, first of all, because it's a biconditional statement. And this is also a key element in Euler's generalization of Fermat's little theorem, like I described in the other series modulo. And I hope to go through some other theorems and formulae using phi in this upcoming series. Pause. So, firstly, we have this Euler product, which is very interesting. It's a product formula designed basically as an efficient way of calculating the value of phi of n, and it was developed by Euler back in the 18th century. And I've spoken about a similar structure before in the prime number theorem series, but this is slightly different. It actually has special meaning in this context of the phi function in number theory. So let's go through an example. Ultimately, I could read off what the formula actually says, but you can see it on the screen. Obviously, so it's better to just see examples for this particular one. Basically, what we're doing in this case, we can actually develop a formula, an algorithm for phi of n based on the primes that divide n, specifically the distinct primes. And the idea behind this is we keep multiplying by a fraction in order to repeatedly exclude all the natural numbers less than n that share that prime as a divisor. And if you think about it in general, this works because we're considering distinct prime numbers, and by doing so, we also rule out all the numbers that share multiple prime divisors with n. And honestly, it helps to write out examples to best see this formula in action. So like where n equals 18, for instance. We know it equals 6, and we can use this formula to verify it. 18 times a half times 2/3, which ends up as 6. But basically what we're doing is we have this quantity, 1 minus 1/2 here. And that represents the fact that we're removing, or in other words, eliminating or discounting all the even numbers, because it's 1 minus 1/2. So all these basically blue shaded numbers, I tried to color them with blue text to make that a little bit clearer, are being excluded. And then alternatively, we also have 1 minus 1/3 as another element in this product. So that means that we're also excluding a third, basically excluding it, we're also excluding a third of the natural numbers less than 18. In conjunction with our exclusion of the even numbers, basically. So in this case, this whole column you might view as also being excluded. Now, there are some numbers in common, like we have 6 and 12, which are both divisible by 2 and 3. But thankfully, this product's formula works out almost in a magical way, in the sense that basically the ratio, we can consider the ratio of all even numbers that are excluded from the set. Well, guess what? The ratio of even numbers that are excluded for being multiples of 3 turns out to equal the ratio of, well, yeah, it would be equivalent to the ratio of natural numbers less than 18 that are divisible by 3. And that is, of course, that ratio, of course, is 1/3. So the key point is that we're repeatedly excluding members of this set based on whether they are divisible by a certain prime number, a prime factor of our number n. And there are different ways of explaining this. But I think I'm fairly sure, correct me if I'm wrong, but I'm fairly sure a valid way of thinking about it is to say that basically the ratio of numbers divisible by both factors, or multiple factors, to the number divisible by just one factor is equal to, especially in this particular case, is equal to basically 1 over that additional prime factor. And that's why this all works out almost magically, in order to give a final result that is equal to the number of natural numbers co-prime to n, because they share no prime factor, essentially. Now here's another interesting formula involving a summation. We have that any natural number is equal to the sigma, the sum, of phi of d for all the numbers divisors d, including n itself. So again, this is one of those concise formulas that's actually very interesting to see. And I'd like to show you the summation in action so that you can see certain examples. So let's check that this is true using this here table of phi function values. So for n equals 5, what we can see is that the numbers in the column phi of I, so 1 plus 4 in this particular case, equals 5. And that's because, well, yes. We can also see this example with other numbers with similar properties. So 1 plus 6 equals 7. And 1 plus 16 equals 17, where n equals 17. And in fact, more generally, if n is a prime number, so if n equals p, then the right-hand side, the sum, will be equal to phi of 1 plus phi of p, because, of course, any prime number is only evenly divisible by 1 and itself. And that's a key fact that comes up, and that kind of keeps recurring in these proofs, I suppose. But the right-hand side, the point is it equals phi of 1 plus phi of p, and we in fact know what phi of 1 and phi of p are. We've established that. Phi of 1 is equal to 1, and we know phi of p is equal to p minus 1. So, again, summing them together, we get p. So that's a verification of this formula where n is a prime number. However, for composite numbers is where you may be less certain that the formula works. So firstly, I'd like to show some examples. For instance, n equals 6. Well, okay, so here you have a listing of all these composite numbers, and we could check every single one of them, or better yet, there's a proof for them, which we'll get to soon. But just to see some examples first, if we chose 6, all of the divisors of 6 would be 1, 2, and 3, and 6 itself, of course. So what we have is 1 plus 1 plus 2 plus 2, which equals 6, indeed. So the box, the values of phi of I that are in a blue box, if you sum them all up, you will end up with the value of n itself, which is in the red box on the left. And so I tried to make that clear through the illustration. So for n equals 12, for instance, we would have the divisors 1, 2, 3, 4, 6, and of course 12 itself. And summing up the phi values there, we get 1 plus 1 plus 2 plus 2 plus 2 plus 4, which of course ends up being 12. And if we chose 18, you can verify that for yourself. So 1, 2, 3, 6, 9, and 18 are all the divisors. And if you take the phi values, they also sum up properly. However, now let's see the proof. So here's an interesting proof. We can consider the partitions, basically, of the set of natural numbers 1 through n. And in fact, we'll define S sub k as the subset of these numbers, each of which has k as its common factor with n, given that k is a divisor of n. So looking at this example, where n equals 30, this is a nice example I like to use, we can list out the numbers of each subset. And I say that D runs through the divisors. You could also say K, strictly speaking. Yeah, strictly speaking, you could say K runs through the divisors 1, 2, 3, 5, 6, 10, 15, and finally 30. However, here's the listing of all these different subsets. Now, at this point, we're just purely talking about sets and subsets. You might perhaps want to verify that this is essentially, basically a partition of the set 1 through n of natural numbers. Basically, the only important thing there, in my view, is basically that each natural number 1 through n is placed in one and only one of these partitions, or parts, I suppose. So, and you can verify that if you want. You can, check that 1 is in only one of these subsets, check that 2 is only one of them, 3 has a unique subset, 5 has its own subset, You can keep doing that. Well, I shouldn't say unique necessarily, but it's in one and only one of the buckets or subsets. And you may notice an interesting thing here, because we can actually consider the sizes of these subsets. For instance, you might notice that the size of S sub 1 equals phi of 30. You might wonder, is there a pattern to be found here? And indeed there is. It turns out that the size of the subset equals phi of n over k. So for instance, S sub 2, and that should say S sub 2, my apologies, equals 8, which is phi of 15, which is phi of 30 over 2. S sub 3, the size of S sub 3, equals 4, which is phi of 30 over 3, excuse me. The size of S sub 5, we can do a similar thing. That equals 2, which is phi of 6. Size of S sub 6 equals 4, which is phi of 5. And we can keep doing this for each of these subsets. And this can be explained by the following. So more generally, we actually know for a fact, for any k and any n that we choose, as long as k divides n, of course, that the size of S sub k of n equals phi of n over k. And it can be explained by the following. Assume that it isn't true. Then there exists a member of the set S sub k of n that is not coprime to n over k. So let's assume, for instance, that what's a good example? Let's say there exists some m, lowercase m, call it, let's say, 12 or something. Just consider as an example 12, I suppose. Assume that 12, actually, see, I don't want to get into too far into specifics, because basically the argument is that, and I hope you listen closely to this, because this is a somewhat important argument, somewhat complex, interesting argument. But basically, assume it isn't true that the size of S sub k of n equals phi of n over k. Well, think about what that implies, right? The reason we say that, the interpretation of this formula is basically that the number of elements of this subset is the number of elements coprime to n over k, basically. So that's the number of elements. And that's because in each of these subsets, we see a pattern where basically, let's say S sub 3, for instance. Well, 3, 9, 21, and 27 they're all coprime to 30 over 3, which is 10. So they're all coprime to 10. So assume there exists a member of the set S sub k of n that is not coprime to n over k. Because we'd have to assume that if these set sizes are not equal, if these, if this equation is false. Then as a result, we know that the subset S sub k shares some additional prime factor P sub j with the quotient n over k. Thus, its greatest common factor with n must be some number greater than k, namely P sub j times k. And if this is the case, then the original number we assumed existed would actually be in a different subset, not the one that we assumed it was. It wasn't. So a contradiction arises, and so we know that the subset must have this property, where each member of the subset is coprime to n over k. How am I doing on time? Okay, I'm doing just fine. And so taking the sum of subset sizes must give us the total number of numbers, i.e. n itself. And we can also write this as n being equal to the sum of the size of a subset, assuming that D divides n. And then by substitution, what we can write is n is this sum, which is equal to the sum of phi of n over d. And since n traverses all the divisors of n, and for each divisor less than the square root of n, there is one greater than the square root of n, the sum is expressible as n equals the sum of phi of d for all the divisors of n. So again, it's a very concise formula and very interesting proof for it, and I'd like to cite a source for that in Mathematics Magazine, Warren P. Johnson. But anyways, there's something called Bezout's identity, and the statement is that whenever you can find any two numbers coprime to each other, call them x and y, then there exists a pair of integers a and b such that ax plus by equals 1. Again, this is one of those wonderful, concise formulas that arises in number theory, and it's extremely interesting, and this is in fact one of the things I hope to describe in more detail in the sequel. So more on this mind-blowing fact and its generalizations and extensions, something called the extended Euclid algorithm, which is very interesting. That'll be all coming soon. So certainly thank you all for watching, and please, again, feel free to correct me or leave comments and questions in the description, or not in the description, in the comments section, whatever. But yes, again, I'll see you next time. Thank you very much.